So what is dimensional regularization? We have seen that ultraviolet divergence comes from this momentum integrals, and d, the number of dimension, plays a crucial role there, and that's why the superficial degree of divergence omega, the formula of that involves d. So if d is equal to 4, then we have a particular set of divergences. Those divergences will not appear in a different dimension. So we set up we formulate the theory in d not equal to 4, and then do our calculations and take d going to 4 limit only at the end. So d not equal to 4, the 4 minus d is going to be the regularization parameter. But when you take d not equal to 4, then lambda is no longer dimensionless. So replace in the original theory lambda by lambda mu to the power epsilon, where epsilon is equal to 4 minus d, and mu is some mass parameter. So the actual theory is in 4 dimension, in which case epsilon must be 0, but we have to formulate the calculations in d not equal to 4, which means epsilon non-zero, and in that case lambda will develop the parameter, coupling parameter will develop a mass dimension, but we want to keep lambda dimensionless and separate out the mass dimension in this form, introducing a mass parameter mu. And how to physically interpret mu, we shall learn on the way. So in the epsilon going to 0 limit, mu disappears from this coupling. So now let's look at the momentum space. Feynman rules. For each vertex, one adds lambda mu to the power epsilon instead of minus lambda mu to the power epsilon instead of minus lambda only. Then you have propagator. Since we'll be doing explicit calculations, we must consider the Euclideanization, and it is the Euclidean propagator. And what we are doing is we had used Euclidean, we had used a bar to indicate that the quantity is Euclidean quantity, but we are removing this bar for notational simplicity. Then the loop integrals will be where d is equal to 4 minus epsilon, right? And then the other parts like overall momentum conservation, symmetry factors, and things like that remain the same as usual. Now, what we will see that since whatever way we calculate this loop integrals, which are being calculated at a d different from 4, and the result will not be divergent. So the region in which this integral is not divergence, we'll call it a domain of convergence. So within the domain of convergence, what we will see is that these loop integrals are given in terms of gamma functions, where d will appear in the argument of those gamma functions. Then the expression will be analytically continued to complex D plane, where it acquires poles in epsilon. So this is an analytic continuation that was rigorously argued by Toft and Veltman. So now we will, given this setup, we shall now look at the Euclidean momentum integration in d dimension, where d is not 4 a priori. So let us compute this integral I of d, which is given by ddl by 2 pi to the power d times a function of the magnitude of L. L is a d-dimensional vector, okay, Euclidean space. Go to spherical polar coordinates, because it is given by the it's rotationally invariant, given by the length of, it's a function of the length of the momentum vector only. So spherical polar coordinates is suitable. So these are the Cartesian components of this L vector, L1 to LD in d dimensions. Then from there, you go to the spherical polar coordinate, where L is the magnitude of that, and then there are d minus 1 angles. One of them is phi and the rest are thetas. L range of L is 0 to infinity. Range of phi is 0 to 2 pi, and range of theta i's are 0 to pi. So the relation between the Cartesian components and spherical polar components are as follows. Then the Jacobian matrix will be given by J del L1 del L del L1 del theta 1 del L1 del theta d minus 2 and del L1 del phi. Similarly, del L2 del L and so on. This results can be easily calculated. Cosine theta 1 minus L sine theta 1 okay, then sine theta 1 cosine theta 2 L cosine theta 1 cosine theta 2 minus L sine theta 1 sine theta 2, then 0 and so on.